Hello, everyone. Welcome to today's seminar. And today we have Dr. Qinghua Zhang from Inria, France. It gives me great pleasure to introduce Dr. Zhang to the audience. Dr. Qinghua Zhang received his bachelor's in 1986 from University of Science and Technology of China and his PhD in 1991 from University de Rennes. He was a postdoc researcher during 1992 at the Automatic Control Division of Linköping University. And I believe during that time he worked with Leonard Leung on system identification. And since 1997, he works at Inria as a researcher, and then since 2001 as a senior researcher. His main research interests are in nonlinear system identification, fault diagnosis, and signal processing. I haven't met Dr. Zhang in person, but recently I found some of his works on adaptive estimation very interesting, and then so we got connected. Had some discussions on research. And it is worth mentioning that Dr. Zhang actually contributed to the earliest version of the toolbox, MATLAB toolbox on system identification some time ago. And Dr. Zhang today will speak on reflectometry-based electrical cable soft fault diagnosis. So Dr. Zhang, please, welcome to the virtual ACFR, Sydney Uni. Please.
Okay, thank you for the introduction. Hello, good afternoon to everybody. So again, thanks for the invitation to give me this opportunity to present my work to colleagues at a so long distance. Okay, so after your introduction, I think that maybe to save time, well, I just pass this very quickly. So currently I work on state estimation robust to unknown inputs and to parametric uncertainties. I also work on sparse fault diagnosis, motion extraction from video images. And I think in the past I worked on nonlinear system identification, statistical change detection, biomedical signal processing, and wavelet networks. Okay, and with some applications and software development. So now let me start the topic of today. So it is reflectometry-based electrical cable soft fault diagnosis. So the main objective of this talk is about electrical cables. We know that now cables are everywhere in modern engineering systems. So they serve both as power lines and as data lines. So we can find them everywhere on the ground, in the air, on water, or underwater. So the first question here is, are cables reliable? So we all know that cables are made of conductors and dielectric materials. So they were considered solid components of engineering systems in the past. But now we know that cables are often installed for decades in hostile, sometimes in hostile environments, and quickly increasing in number and in length. So if well, we think that for a single cable, the probability of failure is very small. But because we have more and more cables and the length increases to, then the probability to have in the system to have at least one of the cables in failure becomes significant. So we can no longer neglect that. So that's why we need some efficient tools to monitor cables. Here are some typical failures of cables. So they may be caused by mechanical accidents, by chemical corrosion, or by some overheating problem. Okay. Of course, it is important to ensure the good state of the good health of cables. Then how to do that? Traditionally, of course, and today we still have this way to do is to simply to have some visual inspection, and we can also do some mechanical fatigue test, some chemical resistance test, or some accelerated test in high temperature. But with this method, typically we need to pick up some samples of the cable. We have to, well, that's not always possible for cables in use. And then we have also the electronic test. So that will be the topic of today. So because cables serve to carry electricity, then we just test their behavior, how they react to electricity conduction. So we use the technique of reflectometry. This is an efficient and non-destructive monitoring method. So the principle is as follows. So we inject a radio frequency wave, and then we analyze the reflected and transmitted waves. So the wave is injected from an emitter here, and if along the path there is some discontinuity or some other variation in the cable, then some part of the waves will be reflected, and this is also the receiver that will capture the reflections. Let me explain the difficulties in this work. So the first one is that typically measurements are made at one end or two ends of a cable. Because typically you cannot get measurement everywhere along the cable. But faults may appear everywhere along the cable, and the cable may be long. So that's the lack of information, the lack of measurements is the first difficulty. But do have easy solutions in simple case. Well, the easy solution is as follows. Assume that the cable is cut somewhere, and you, of course, the current is stopped. It is easy to know that the connection is lost. But we can also easily know the distance where the cable is cut, because if you send a short impulse, the impulse right to the end where the place where the cable is cut, and then it gets back. You just count the time, the round time traveling time of the wave. if you know the speed of the wave, then you can compute the distance. So that's the idea. So it does work in this way. Now you can buy instruments commercially to do this job. Okay, it works quite well. The second difficulty is related to multiple reflections. If there are more than one discontinuity in the cable, then the waves may go back from one discontinuity, go back, and then will be reflected again and again. Yeah. So and every time, only part of the wave is reflected, and the rest will go through the discontinuity. That's why we'll at the receiver we'll find some fictive reflections. That makes the problem difficult. Okay. The third difficulty is related to the fact that most methods focus on the detection of discontinuities in the cable. Well, I also talked about discontinuity in my introduction up to now. Such methods are not applicable to soft faults. Soft faults, I mean, it is caused by weak discontinuities or with no discontinuity at all in the cable. This is an example. For a twisted pair, if you, at some position the cable is untwisted, there's no discontinuity, but only some smooth modification of the configuration of the cable. In this case, the method looking for discontinuity won't work. But in such difficult situations, we have to use model-based method. Model-based, unfortunately, there's a well-known mathematical model of electric cables. It is obtained. It can be derived in this way. So if you discretize a long cable into small segments, each small segment is modeled with 4 simple elements. So a resistance, inductance, a capacitor, and also this is a conductance. It is for the conductance between the two conductors. Is this isolation material that may have some very weak conductance. And then from this discretization, while each segment has its length turns to 0, then we'll get this equation. Well, of course, V is the voltage and I is the current. Now these equations are called the telegrapher equations. Okay. With this formulation, the faults that are modeled as sparsely distributed parameter twins. There are these 4 parameters, but these parameters depend on the position on the space variable G. So these are 4 functions of the space. So that are called distributed parameter. And then the fault diagnosis should monitor the variances of these distributed parameters. Of course, it is an inverse problem. It means that we only have the data collected from 1 or 2 ends of the cable, and then I try to compute the parameters. So I said that these equations are called telegrapher equations, and we are interested in these parameters that may vary along space. I talked about, already mentioned the inverse problem, where because typically such a model, the model of telegraphy equations are used for simulation. So the simulation problem is the so-called direct problem. It means that given these equations and the parameter values all along the cable, and if we are given the initial condition and also the boundary conditions, I mean, at the left we have some source, and the other side had some load, and with the initial condition, then a simulator can solve the telegrapher's equations to simulate what the current and the voltage all along the cable, and also in particular the data collected by sensors at one or two ends of the cable. Then the inverse problem is as follows. We only have the data collected from one or two ends of the cable. We want to know what are these distributed parameters. When talking about the inverse problems, typically in most methods, not only restricted to cable monitoring, but in general, most methods are based on model data fitting methods. So you can imagine that you define some criterion that explains the data with the model, and then optimize the criterion. Typically, you get ill-posed problems because you have many unknowns. Many unknowns because typically you have distributed parameters. And such methods are also highly computationally expensive. Now here, I will present a quite different approach. So they are really efficient, very fast. They can also do fault diagnosis in real time. Well, typically, we consider, well, of course, there are four parameters. We cannot do all of them. Anyway, it can be proved that these four parameters are redundant. It should be reduced to 3. And the most important parameter for a cable is the so-called characteristic impedance. It is defined like this. Oh, sorry, I forgot the square root. Here, the square root. Okay, so Z0 is the square root of I over C. It is called the characteristic impedance. So for engineers, this is the most important parameter of the cable. For this problem, for the estimation of the zero of Z, we have implemented a real-time inverse scattering algorithm, and it is available as a software. It is called ISTI. So I will show you a demo today. Another important problem is to estimate the parameter R. So R is the resistance all along the cable. So it is a parameter about the ohmic loss of the cable. We also fast solution to this problem, and it is patented by Inria and an industrial partner. So today we will talk about this problem. Okay, so again, the square root sign is missing here. There's also ongoing studies to study conductance estimation, it is more difficult because it has a very, very small value. So typically it is 10 power minus 10 in the standard unit of the conductance. So conductance, in fact, is the inverse of the resistance. So while we are interested in the characteristic impedance, so again with the square root here. So because in most cables are in good quality, the resistance and the conductance are almost zero. Some typical values for very ordinary cables, R is about 0.01 ohm per meter, and G is very, very small, really small, okay, almost zero. So in such situations, the so-called inverse scattering theory provides an efficient solution. So what is the inverse scattering theory? Well, it has been mainly studied during the 1970s and 1980s for the analysis of nonlinear wave equations. So it is in particular about the so-called soliton wave. So soliton wave are a very particular kind of nonlinear waves that can keep some impulse form at a long distance. So this theory was developed during that period for the soliton waves, but recently it is applied to cable photodiagnosis. So we just borrowed this theory in some sense. To quickly give you some idea how it works, the theory. So we start from the telegrapher's equations. It is in the time domain, and then we pass through the Fourier transform to get the same model, but in the frequency domain. Now I have to introduce what is called the frequency domain reflection coefficient, because this is what we can get by the sensor, by the emitter and the sensor that gives this value. It is called the reflection coefficient as a function of the frequency omega. So it is defined as follows. At the left end of the cable, we can observe the voltage and the current applied to the cable. With this is an emitter and also receiver. So we know the voltage and the current at a certain frequency. So assume that we apply just a sinusoid signal. And G ref is the reference impedance, that is the internal impedance of this this instrument. Okay, and the incident wave, the wave that is traveling in the in forward direction, is computed like this. And the reflected wave is almost the same, but with a sign, minus sign here. Of course, if you divide the denominator and the numerator by I, everything is divided by I, then you get only the Z ref here, and you get another impedance, is the total impedance of the cable here. So this is another formula for the so-called reflection coefficient. That is a function of the frequency. So the problem we want to solve is as follows. We know the reflection coefficient as a function of the frequencies given by this instrument. And then we run an algorithm that will compute the characteristic impedance. Now this time I do have the square root of L over C. And then this is the so-called inverse scattering algorithm. So with the well, it starts with the reflection coefficient here, and then we use the Fourier transform to compute the rho of x. Rho of x are here in this pair of integral equations. In this equation, the A1 and A2 are unknown matrices. Matrices for double variable functions of x and y. And well, we have to numerically solve these equations, and then it can be shown that the impedance is related to A2 through another function Q over x in this way. So it is difficult to prove this algorithm mathematically, but well, this theory was already known. So I said that during 1980s. So this theoretic solution was proposed in Zhang well, it was a French physician proposed this solution, but for infinitely long cables. So it was only the theory. So our recent work established the connection between this theory with real-world finite length cables and also with available sensor signals. And then we experimentally validated this method. I think that, well, now I can show you a video of the demo. So in this demo, you will see that we use a network analyzer to test the cable. This is a meter and also receiver that will give you the so-called reflection coefficient, and then we use the software to compute the profile of the Z0 as a function of the space, and the variations of that interconnection is and some local forces. Opportunity to visit able to see the because here I can only do the video. Do you see the video demo?
Yes, I can see it.
Okay, thank you. So these are the signals, the reflection coefficient, the absolute value, and the phase. So this is computed in real time, the curve of the impedance. So here you have localized fault, and the effect of the fault is visible on the curve. And in this example, there are two. Well, we'll create another fault. So in real time, the curve reacts to the fault we created. And this is the distance is 3 meters and 4 meters. So the fault is between 3 and 4 meters, and it is somewhere here. So this is 3 meters and 4 meters. Okay, so that's all about for the demo. Okay, so let me conclude this talk. It is about cable fault diagnosis. So we applied the inverse scattering algorithm to monitor the cable. So it is an efficient tool for soft impedance fault diagnosis. So that is important because most methods focus on discontinuities, but in the example I showed you, there's no discontinuity. We also have a result that extended to this result to ohmic losses. Now we are working on new, more difficult problem as the dielectric failures. Okay, so I was just concluding that today I talked about the impedance for the diagnosis, and then currently we also have another result that extended this result to ohmic losses. Now we are working on the dielectric failures that is more difficult. And we are also working on complex networks with partial node measurement. Well, about network monitoring, we do have some results now. It is either for simple networks with single node measurement, or we can also work with complex networks, but now we need full node measurements. So the challenge is to work with soft fault in complex networks with partial node measurements. So, this is a much more difficult problem. Okay, so that's all I want to say. So thank you for your attention. I have finished.
Thanks, Dr. Zhang, for the very interesting talk. Are there any questions from the audience?
Yeah. Thanks very much for an interesting talk. I think it was, sorry, let me share my screen as well on my video. Hi, oh yeah. The results you show are very similar to results that you could obtain with a normal high sensitivity TDR that uses either a very short pulse or a chirp to determine small changes in the characteristic impedance of that line. So can you differentiate between your technique and a typical TDR type response? I know you discussed it at the start, and you suggested that TDR was only suitable for complete discontinuities, but that is not in fact the case. Any small change in impedance will result in a reflection of some of the power, and you can extract the echo from that.
Yeah, you are right that you can, well, impedance variations will give some reflections, but what we have done is that we can really compute the impedance curve, the characteristic impedance curve from the reflections. That's the main difference. I think that typically people capture the reflections, and then it is if there's no clear discontinuity along the cable, it is hard to interpret the reflections.
Okay, so you're saying your system, your technique is much more sensitive than basically just a normal examination of reflections.
well, I would not say it is more sensitive because we use the same instrument, but the result is easier to be interpreted because we directly give the curve of the characteristic impedance as a function of the space.
Okay, yeah, no, that sounds like a good answer. Thank you.
Yeah. Thank you.
I've got a question. I'm wondering whether the soft faults, like the twist pattern that you show, will they cause problems in the long run, or they just, you know, they just stay there?
Wait, the untwisted pair, this example. Well, it is because it's easy to do for the demo because we can easily create this this kind of fault and then we can repair it easily. Okay, because in real world, typically faults are different, but any fault that modifies the localized the local impedance, and then with this method, we can capture it.
Okay, so this is like soft faults is like is like a ground truth for you to compare when you're testing the algorithm. Okay, okay.
Well, because it is a simple demonstrator, we want a way to be able to easily create a fault, and then we can repair it to reuse the material. Oh, that's the idea. Okay.
Okay. Thank you.
So can I ask another question, please?
Yeah, of course, please.
Thank you. You've shown this result for an electrical system. Now, I know that there are major problems that occur in looking for soft faults in pipes and underground, or mostly underground pipes. Could you use an acoustic equivalent of this to actually find sort of discontinuities in pipes as well?
Well, I did have thought about tried to do something like that. Well, in theory, well, this method is based on linear wave equations. So in theory, it should work. But in practice, the trouble is as follows: it's a loss in the pipelines. If well, that depends on what kind of wave you use. Probably, for example, you will use acoustic waves.
Yeah, that's the idea. A compressional wave.
That may work, but even in that case, if you have many loss of energy, and then you will only capture very quite weak reflections, that may be the trouble.
Okay,
I mean, if there is no failure in the pipe, but you only get a very weak reflection, then you get very little information about the pipeline. But we do want to do something like that. We are trying to do some experience.
Okay, thank you.
Okay.
Are there any questions from the audience? If no, then please join me in thanks Dr. Zhang for this interesting talk. Thanks, everyone.
Thank you.
Thanks very much, Dr. Zhang.
And if you want to stay longer for a chat, then please stay. If Dr. Zhang has time to stay
I can stay a little bit with you.
Yeah.
No problem.
Sorry, I've got other engagements, so I can't stay on the line after this. So, but thanks very much. It's an interesting I do radar work, so it's an interesting extension to the work that I normally do. So
thanks, Graham.
yeah, it makes me think about other methods that I could be using to work on radar systems, because we have the same problem with waveguides. Looking at losses in waveguides and looking for discontinuities, and I presume, as you said, that the equations, they're all linear equations, so we could actually apply those.
But you are talking about Wi-Fi is in the three-dimensional space.
That's right, yeah.
Unfortunately, I do not know the theory in three-dimensional.
No,
okay.
Neither do I, I'm afraid.
I think that, well, many people have already tried that, including me. But
Okay.
no, I do not know the solution. Well, indeed, mathematically, it was a kind of, well, I think that in some sense, we were very lucky that to find this result from the soliton theory.
Mm-hmm.
So, well, the result in soliton theory was really fantastic. I cannot imagine how the mathematicians have discovered that. It's really fantastic. But it is only in one dimension. I think that many people have already tried to generalize the result to 2D or 3 dimensions. But well, I haven't never seen any publication about that. And myself, I think that it is really difficult. Well, I would not say impossible, but really difficult. I have no idea how to do that.
Well, if you think of nature, you only see solitons in one dimension, or mostly. I think in fiber optics you can get solitons generated in nonlinear fiber optic cables, and that I would have thought was 2-dimensional.
Do you mean the theory is generated to 2 dimensions?
No, what I'm saying is actual solitons. Basically, if you think about where solitons are used, they're used basically to maintain the coherence of short pulses in fiber optic cables.
Yeah, I know that. But here we are not really using in the inverse scattering solution to the cable for diagnosis. We do not really use something directly related to solitons. Okay? So the inverse scattering is only part of the solution to soliton equations. We only use this part where it is not all about soliton. We were really lucky to find this part of the soliton theory.
Okay, no, I understand. Yeah.
But I do not think that soliton theory is already generalized to 2 dimensions. I don't think that. And I looked at that about 10 years ago. Maybe I should try again to see there are some new publications.
Yeah, look, I don't know enough about it. I've read a little bit about the fiber optic stuff, which might actually be, you might actually consider it to be a 1-dimensional problem because the actual fiber is homogeneous across its cross section. So I don't know. Anyway, I think that's pretty much all I can think of. So thank you again for your time. It's been a very interesting lecture. I've appreciated it. Thank you.
Thank you, Ryan.
Cheers.